Okay, so then I'll start. So I welcome you to this problem solving and live interaction session for the subject engineering mechanics offered by Professor K. Ramesh on the SWAYAM portal. So today we will be discussing the contents of week 5, which has to do with virtual work, principles of virtual work, and energy relations. So before we begin, let us look at some aspects to virtual work. Essentially, how is work defined in mechanics or rather physics is it is the dot product of force and displacement. So if we have two vectors and let this be some theta, so we know that the projection of this vector onto this and the is what is denoted by the dot product. So if I were to represent this as vector A and this as vector B, so A dotted with B is essentially magnitude of A, magnitude of B cos theta. So this is how work is defined. The units of work is same as units of moment, which is Newton meter, but it is essential to understand that it is fundamentally different from moment in the sense that work is a scalar quantity and moment is a vector. So when we come to virtual work, essentially there are two ways to go about. One in which we take the displacements to be unknown and then we try to relate them. So that will be the displacement method where we will give the system a virtual force and the actual displacements will do some virtual work. The second way to go about is we have forces acting on a system and we want to analyze the equilibrium of that system and relate the forces. In such a case, we give the system a virtual displacement. Even that gives you a quantity of virtual work. So we can see that if there is a force, we give its corresponding displacement. This is just the analog of its corresponding effect. Force brings about displacement. Translation can be decomposed into two or three components of displacement depending on whether it's a planar problem or a three-dimensional problem. Similarly, moment brings about a rotation. So that is why moment is dotted with its corresponding virtual displacement, which is delta theta. So what in a general system there could be forces and moments acting. So this is the most general form of the principle of virtual work, where we will consider essentially this, where we will give it virtual displacements and we will try to relate the forces. So the virtual work is defined as the dot product of force and the virtual displacement and moment and the virtual rotation. But for our general purpose, we will call this as the generalized force system, which will contain both forces and moments. Okay, so this begs the question, why do we need to have virtual work? Why do we need to study this when we can simply deal with force equilibrium? So this gives us an alternate way to analyze systems where the systems are given arbitrary meaning that is it can be given at any point and it can be related, infinitesimal, needless to say it is very small, and consistent virtual displacement. So we'll discuss what consistent means. We should not violate the constraints of the system while giving virtual displacement. Otherwise, the problem does not actually get captured into the principle of virtual displacement. We are essentially solving some other problem. So we should be consistent with the constraints given to the system. That is what this consistent implies. The force that act during the virtual displacement produce virtual work. Now, this is important to understand that when we go to a system, all this will become clear because right now we are just covering the theoretical framework of this, and once we will go and apply this to some problem, it will become clear. But what I want to emphasize is it is the actual force that is applied to the system which is given a virtual displacement. Now, this might beg a question, what causes this virtual displacement? Because displacement just cannot come about. We have to give some force which caused a displacement. So that force we do not account for. That is some external agency. That is, if we have a system, we introduce a virtual displacement by giving it a virtual force. But in our analysis, we don't consider that virtual force. Once we have introduced Yeah, Mr. Krishnan, could you just mute your mic, please? Thank you. So once we have a system and we have introduced a consistent virtual displacement, we will be analyzing the effect of the actual force under that virtual displacement we have introduced, which will become clear as we go about. Another thing to essentially understand is sign of the resultant work should never be put arbitrarily. It will depend on our dot product. Meaning, if we have a virtual displacement and our, let me just clarify this. Let us say that we have introduced, there is a force acting like that on a system F. And we have introduced a virtual displacement like that. This is delta U vector. In this case, we are able to see that theta is less than 90 degrees. Therefore, its virtual work is F dot delta U will be positive. At the same time, if I have a system, in the same system, if the force were acting like that, and if I introduce a displacement, virtual displacement like that, we are able to see that theta is greater than 90 degrees. Therefore, virtual work is force dotted with delta U, which is negative. So once we give virtual work, we should analyze the active forces which are on the system, whether they are doing positive virtual work or negative virtual work, and appropriately put them in our equations. Only then we are solving the correct problem. Generally, what is done is we don't complicate it by considering dot product always. So we just say that if the force we have introduced is in the direction, its projection is in the direction of the virtual displacement, it is positive virtual work, and if it is the other way around, it is negative virtual work, which will become more clear when we go about. Okay, with all these discussions, what are we trying to do? We are trying to analyze a system, basically a mechanism, the equilibrium of a mechanism. So virtual work gives us positions of equilibrium. Meaning, if I change one of the forces, how does the system as a whole change its configuration to bring about equilibrium to that system? This is what we are trying to analyze in the using the method of virtual work. So a mechanical system is said to be in equilibrium if the work done is negative or zero under every small virtual displacement. So we will take a system, we will give it a virtual displacement. There will be active forces on that system. We'll discuss what active forces are. Once those active forces do some work, we'll try to relate all the work and add it up. The total work, if it is zero or if it is negative. Negative case we will not take because that has to do with friction and all that. We'll essentially be dealing with the virtual work saying that total total of all the virtual work contribution of all the active forces, if it is zero, then system is in equilibrium. Till now, what were we trying to do in the analysis of rigid bodies? We were trying to find out the internal forces, or we were trying to find out reaction forces. All these we were doing it with the help of the constraint that the system is in equilibrium. Now we are trying to analyze the same systems using a different method, because it will be more convenient to solve a system of rigid bodies using this method. And there are some particular class of problems where this becomes a necessity. This is what we will see, that the sum total of the virtual work done by all the active forces in the system, if it equals zero, it is in equilibrium. On the contrary, we will take that it is in equilibrium and equate it to zero and find out our active force relations. Okay. So we have arbitrary, consistent, and infinitesimal virtual displacement is what we will give. So if we look at this system on the right side, it basically has a hinge here and it has a roller support here. So we know that roller basically gives a constraint like that. If we were to take it, so it will be having two forces like that, the reaction forces by the pin, and then it will have one reaction force like that, because the roller is essentially giving only one restraint. Now, if we were to give a virtual displacement like that, essentially what we are saying is the roller has lost contact with the wall. At this point, we are saying that this contact over here is no longer there, no longer present. So we are violating some of the constraints of the problem. So we are essentially solving some other problem. We are not solving this problem because we are not respecting the constraints given in this problem. So our virtual displacement introduced has to be consistent with the constraint of the system. Only then we will be solving that particular problem. So that is something we need to keep in mind. I'll just give this brief about virtual work for about a few more minutes, and then we'll delve into problems. So please bear with me, because this background is essential so that we don't have questions popping up when we actually solve problem regarding the fundamentals. Okay, so we have seen what we call as generalized active forces is moments and forces put together. That is, if we have a body, if we have some body and it is applied with forces and it is applied with some couples, the entire force system is what we refer to as the generalized force system. Now, in this generalized force system, what are active forces is what we are trying to see. Active forces essentially mean the virtual work contribution by them is non-zero, meaning the virtual work contribution of the forces which is zero are inactive in the system. They are not acting as such. Okay, so the question asks, let us look at this question. How many generalized active forces are present in the system shown that contribute to virtual work due to a consistent virtual displacement? Now we have seen what will be the consistent virtual displacement with this. Can it go through the floor? If I give a virtual displacement like that, it cannot go through the floor. That is for sure. Another thing is, if I were to lift this up, even then the roller loses contact with our floor. In essence, we are not respecting the constraint of the system. Now, if I were to give a virtual displacement like that, let us say, then we are not violating any condition. So I hope that that is clear. Now, this is a valid virtual displacement. Now, if I were to have the floor to be horizontal like that, under the action of this force, it is essential in the method of virtual work, it is essential to visualize the deformed configuration of the system. So let us do that. So the deformed configuration of the system would be something like that. It will be something like that. If I were to draw just the center line under the, so if I name this theta, this has become some theta dash. It has increased, and that increase can be related to delta U. So in such a case, as this force will be applied here. So this force has actually undergone this much of displacement, virtual displacement. At the same time, this moment, we know that it has undergone theta dash minus theta, virtual displacement it has undergone. This force will be applied over here. So we can see that its virtual displacement is also non-zero. However, now let us consider this force that is applied on the roller. We are able to see that this is 90 degrees. So will this be contributing to any work? Essentially, the dot product is zero. So this force, I'm sorry, 1 minute. So this force does not contribute to any virtual work. So hence, this force is not an active force in the system. In that case, how many active generalized active forces are there? I have a force here, I have a force there, and I have a moment there. Now we can ask, what about the reactions here? I'm able to see that the pin over there, it does not have any displacement. So essentially its contribution is 0. Whereas this roller, although it does have a displacement, that displacement is perpendicular to this for active force applied, hence it is not an active force. So we can see that 1, 2 and 3. There are 3 active forces in this system which are contributing to virtual work. Are there any questions at this stage? Okay. So if you do have questions, you please feel free to ask midway. We can take it like that. In the meantime, I'll move forward. Okay. All right. Now let us look at this concept of degree of freedom. Yes, please. Yeah. See, do you agree that under the action of this delta u, do you agree that theta will increase to theta dash? If theta increases to theta dash, what is virtual work by m? Virtual work contribution by m is m delta theta. So what is delta theta? It is essentially final minus initial in a way. Final minus initial, right? In such a case, when this is non-zero, you have agreed that theta dash is higher than theta, which means delta theta is non-zero. M I have applied, so I know it is non-zero. In such a case, this quantity is non-zero, is it not? So when the virtual work contribution is non-zero, it is an active force. Active, generalized active force. Okay, yeah. I think your confusion was whether to call moment a force or not. Moment is not a force. Let me be clear. Moment is a generalized force. In a general system, there can be forces as well as moments. For the sake of counting, we are just calling it generalized force system. Okay. So I hope that that is clear. All right. Okay. If that is clear, you can unraise your hand, and then when you have a doubt, you can raise it back again. Okay. Yeah. So let us see what degrees of freedom are. Now we have been asked, consider the assembly of the rigid body shown. There are 3 links that are connected like this, and we have been asked to uh, find out how many degrees of freedom are there. So what essentially are degrees of freedom? These are essentially some coordinates which define the system fully and are independent in nature. So let us say that I have a bar like that. Okay, so let me take a link like that. Now we are dealing with planar systems. In general, in a 3-dimensional space, any body can translate in 3 directions and it can rotate in 3 directions. So generally in space, a body has 6 degrees of freedom. Now we are confining our attention to the plane of this screen. In such a case, what are the degrees of freedom that are active that this body can undergo? One, it can translate vertically, it can translate horizontally, and then it can rotate about the axis that is coming out of the plane. So a rigid body in a plane has 3 degrees of freedom. I hope that is clear. 2 translation and 1 rotation. So far so good. So this rigid body has 3 degrees of freedom, which is 2 translations and 1 rotation. I'll just make a copy of this so that I can use it later. Okay. All right. Now what I have done is I took this system here and I put a pin here and I put a pin at this point. So what does the pin do? Pin allows rotation. We have seen in our previous discussions that pin allows rotation but arrests the translation totally. So once this pin was introduced, pin, it essentially took away 2 degrees of freedom. It took away 2 translations. It allowed only rotations. So now this system, once we have attached it to the pin, we have this theta. So this theta can vary. It can still rotate. So this pin, what it does is it can still rotate about that pin, but it cannot translate anywhere. So this system has 1 degree of freedom now, because initially it had 3, now it has only 1, wherein it can rotate. Okay, now what we have further done is we took another link and then we put it here and then we put a pin there and then we put a pin there. Now what can the second link do? Can it translate with respect to the first link? No, because there is a pin there, but it can rotate with respect to the first link. It still can rotate. It can still rotate like that, but it is not free to move. It is not free to have translation. So essentially, this link has 1 more degree of freedom. From this, we can extrapolate for the third link also, it will have 1 degree of freedom. Third link is like that, let us say. Now this link again can rotate like this, but it cannot translate with respect to the second link. So it has just 1 more degree of freedom. So what are the total degrees of freedom for this system? There are 3 degrees of freedom for this system. Meaning that I have to mention at least 3 quantities to correctly identify where each and every particle in this system is. Is that clear? Are there any questions here? Yeah, please go ahead. Oh, you are saying it is clear, is it? Okay, I suppose you are saying it is. Okay, all right, thank you. So this is how we analyze for degrees of freedom. For now, we will be looking at systems with single degree of freedom. But this is the basis for analysis. In case of systems with more than 1 degrees of freedom, we can write virtual work equations as many number of times as there are independent degrees of freedom. So I hope that that is clear. So this has 3 degrees of freedom. Okay. Now let us look at this question. The principle of virtual work is best suited for solving problems dealing with which of the following? Particles, a single rigid body, system of interconnected rigid bodies, or internal forces in a member. Now it is surely not particles, because sigma fx equal to 0, sigma f vector equaling 0 is the, yeah, right. It is exactly system of interconnected rigid bodies. I'll just explain why that is. So if we have a particle, if we have forces, we are essentially giving a displacement to this particle and then counting up all. It is tantamount to doing the vector sum, which is equaling 0. So particles, it is not much used. For a single rigid body, we have been dealing with single rigid bodies only till now. First of all, we took a truss as a whole. We found out the reactions. So those are much easily dealt with normal equilibrium equations. Whereas when we come to system of interconnected rigid bodies, let us say that I have 2 systems like that. And I have a pin here and I have put a roller here. And then I connect it with a spring. And then I apply some force. Now, depending on this force and this spring constant, this system will attain some position of equilibrium, which is not very convenient for me to analyze using our normal statics force system equilibrium, which we have been doing till now. Whereas this system, which is a system of interconnected bodies, it is easily, we can analyze that using virtual work principles. Even if the spring were not there, we can see that this is a mechanism. This is no longer a truss. So for the analysis of mechanisms, principle of virtual work comes in handy. So mostly we have mechanisms made up of multiple rigid bodies interconnected. So system of interconnected rigid bodies is best solved using the principle of virtual work. Now there will be one more question that one can ask, that why internal force in the member cannot be analyzed like that. So let us look at why that is. Let us take this to be one body, and let me give this body a virtual displacement like that. Let us say that I have given a virtual displacement like that, such that this body would have gone there, but I'm not drawing the final configuration. You can just gauge it that I have given it like that. Now what I'll do is, I'll take a section here. Let me cut a section there, and let me separate out these bodies. Now this is free body 1, this is free body 2. Now there will be some generalized force acting on, let us say it is this way. This is force acting on 1 by applied by 2. From Newton's third law, we can see that there will be, this is force applied on 2 from 1, which will be equal and opposite. It might not look equal and opposite. Let me make it look equal and opposite. These two are equal and opposite. I hope you understand that. In such a case, the virtual work done by this force will be nullified by the virtual work done by this force, because we have to take for the system the virtual work done. That is why when we separate out members to expose the internal forces, from Newton's third law, one becomes the opposite of the other, and work is a scalar quantity where our dot products can be positive and negative. So essentially, if this dot product is positive, this will be equal and negative, which will cancel out the effect. So I hope that that is clear. Okay. We are just building up to it, and soon we will be entering problems. Okay. So which of the graph captures the essence of the principle of virtual work correctly? So what do these graphs represent? Essentially, the shaded area represents work. It is the area under the curve, so that essentially represents work done. Okay, so in such a case, which of these is representing the correct principle is what we have been asked. No, now here what we are saying is virtual work is, for the first case we are saying virtual work is virtual force into virtual displacement, with the understanding that delta R is the virtual displacement. This is the first case saying. This is saying that delta F, I'm sorry, this is saying half of that, because the shaded area is a triangle. So area is half of that, right? This is delta R. This says virtual work contribution is F delta R by 2. And this says virtual work contribution is F delta R. Now D, yes, exactly. So we'll just quickly see why that is. See, here what we are saying is virtual work is caused by virtual displacement is caused by virtual force, which we said was not the case. We will be giving a virtual displacement by some external agency, which is out of our analysis. So these two certainly cannot be coming together. So these two certainly cannot be the answers. Now coming to these two, what this implies is actual force, active force I should say, force has caused the virtual displacement. This is what this statement says. Why? Because as I apply my force, my displacement is increasing. So this seems to imply that my force is what is causing the displacement, which is not the case. Whereas I have a system where one active force is present, and then I gave it a virtual displacement by some external agency. And the work done by this system, by this active force under that virtual displacement is what is our virtual work contribution. So this is our answer. So whosoever said that is correct. So I take it that this is clear. If there are any questions, I suppose if there are any questions, you yourself can ask midway. So I'll keep moving on. As and when you have any questions, you please feel free to ask. Which of the following is or are true with regard to the method of virtual work? Is our question. There is no need to visualize the deformed configuration of the assembly. This is certainly not true. There is absolutely a need because we should give consistent virtual displacement, and without visualizing we cannot find out whether the virtual work contribution due to an active force is positive or negative. Essential to find out delta W is positive or negative, and only when we accommodate that positive and negative nature are we solving that actual problem. So this is very essential to visualize this. Even without this, for engineering acumen, one should be trained to visualize deformed configurations. Okay. The relation between the active forces can be determined without first determining the reactive forces. Now, in one of the questions, we saw that reactive forces are not doing any work. So when we sum up W external and equate it to 0, this does not have reactive force contribution. While it has all the active forces existing in the system. So definitely without determining the reactive forces, we can find out the relationship between active forces. There is generally no need to isolate individual members of the assembly for the analysis. We just saw here that when we isolate the individual members, we actually took one member and then sliced it into two. Let us say that if the system was such that it was articulated here, meaning two rigid bodies were connected here. If I separate them out, it will still be the same case, that the second rigid body is applying F12, first is applying F21, and both are equal. If we even dismember it, we will see that both the forces that are coming as a consequence of Newton's third law are making no difference to the equation. So yes, there is actually no need to do this. If we dismember it, it is not going to help us in any way. There are no restrictions on how to introduce virtual displacement. We have discussed this enough that it should be consistent with the constraints of the system. We should respect the constraint of the system to solve that problem. Positions of equilibrium can be analyzed under the known loads. Yes. So for example, we saw this problem. Now, for some force, when will this come to come to a halt, or what will be the position of equilibrium is what we are trying to see. So yes, actually speaking, there should be a constraint here, because we can see that this offers only vertical restraint. So what I had drawn initially, that spring, is much required to keep that in equilibrium and at some configuration. So how to find out what is the, let us say, what is this theta when it attains equilibrium is the kind of question we can solve with this virtual work. So positions of equilibrium can be determined under the action of the loads. So, okay. So I hope that this is clear. Now let us see a very, very mundane application of this problem first. We are trying to find out what is the minimum force P required to hold the uniform iron bar weighing 250 newtons in the position shown against the smooth surface. So these are smooth surfaces, meaning there is no friction. Okay, so we have been given that there is a link like that. Let me just draw it like that. And then there is its force 250 Newton acting. If I draw its free body diagram, it will be something like this. P, this is N1, this is N2, both given by the floor. And there is no friction in the system. And this is given to be some theta. Theta is given to be 36. I'll just take it to be theta for now. Now, we can see that this cannot translate vertically, nor can this translate horizontally, but it can surely rotate. Now, what is the another configuration that this can have? I can have this going there, and then it comes over here. This is, I'm not drawing the actual link. I hope you can understand what I'm trying to say. That if under the action of this, it can either move this way or it can go down. In such a case, we can see that N1 and N2 are not doing any virtual work. If this be my virtual displacement, these are not doing virtual work because these are perpendicular to the virtual displacements. So these are not active forces. So essentially what I have here is, this is my free body diagram. This is my free body diagram. Now what I'll do here is, I'll just make a copy of this and remove the forces that are not doing any virtual work. So this is known as the active force diagram. So now we have come up with the active force diagram. This is L, the length is L. Okay. Now actually our question asks what is the minimum force to prevent it from falling. So the actual configuration would be something like that. It would have gone here because it is falling, and then my force will be applied like that, and the mass weight which was here, it would have come here. So this is the virtual displacement I have given for weight. This is the virtual displacement for mg, and this is the virtual displacement for force P. Now this is a single degree of freedom system. So both these delta UP, delta UMG can be related. That is the entire point behind this. So if this distance, I can calculate this, what will this come out to be? L by 2 sine theta. Let me call this H. That is, this distance is H. And this is the fixed wall. From here, let me call this distance as D. So when H moves, when we give a virtual displacement to H, mg will do some work. When we give a virtual displacement to D, force P will do some work. So let us see what that is. Now H, from our geometry, we can write H to be L by 2 sine theta. And we can write D to be L cos theta. I hope that is clear how we have written that. H is L by 2 sine theta and D is L cos theta. Now to do virtual displacement, what we will do is we will just differentiate this. L by 2 cos theta delta theta. So essentially delta theta is our virtual displacement we have given here. This delta theta is the virtual displacement we have given. Similarly, if I differentiate this, delta D will come out to be minus L sine theta delta theta. Now, one thing to remember is that we should always take magnitudes. Always consider magnitudes of virtual displacement. And assign the sign to virtual work based on physics of the problem. I'll just explain what I mean. This delta D is giving me a negative value. Now, if it so happens that I had given a virtual displacement where this was going up, where theta was increasing, this quantity will still give me a negative work contribution. That is why we should not do that. What we should do is, therefore, first I will consider delta H, magnitude of delta H, which is L by 2 cos theta delta theta. And then I'll consider magnitude of delta D, which is L sine theta delta theta. Once, I'm sorry. Once I have this, I can proceed with my general principle of virtual work. What does that say? That the sum total of the virtual work done by all the sum total of the virtual work external is 0 for it to be in equilibrium. What our question is asking? Position. To hold the uniform bar in the position shown, meaning to maintain equilibrium. So to maintain equilibrium, to apply the principle of virtual work, it says sum total of all the virtual work is 0. So if I add up the virtual work due to mg, now I can see that under the action of this delta, this is delta theta, my mg, or I should say mg here, or 250 newtons or whatever, 250 newtons and the virtual work which is going down, these are both in the same direction, because I am considering the bar to be falling. So this will give a positive contribution. Whereas here my force is applied to the left. My force is applied like that, but my displacement is going like that. So the virtual work contribution of P will be negative. This is what I meant by analyzing the physics of the problem and assigning the sign. So what this means is delta W of the weight mg minus delta W due to P is equal to 0 is what this means. So this will be mg is, let me add one more page here. Mg is 250 Newton into delta H minus P into delta D equal to 0. This is where I have applied my principle of virtual work. So I have said there were two active forces we saw. One was the weight, which is 250. One is P. These are the only two active forces, and these have done work, virtual work, and the virtual work contribution of P force is negative. The virtual work contribution of 250, which is the mass, which is the weight, is positive. I have written this. Now I have to replace these two in terms of a common denominator so that I can analyze. That is what we derived here. So let us go ahead and substitute this. So it is giving 250 into L by 2 cos theta delta theta minus P. What was the other one? L sin theta delta theta. L sine theta delta theta equals 0. So what will this give us if we solve this? 250 L by 2 cos theta delta theta equals PL sine theta delta theta. Now I have given an infinitesimal virtual displacement. So surely I can cut these out. It will not give me that 0 by 0 problem. What else can we eliminate from here? We can eliminate L from both ends. And then I can take this sine theta over here. So I have got P as 125 by cot, tan theta. So we have got a relation for equilibrium. If I give any theta now, for any given theta, I can calculate what should be my P so that the system is in equilibrium. So I have related the active forces like that. Now in our question, we have been given that theta is 36 degrees. So all we need to do is substitute that. This is general equation. General condition for equilibrium. Specific to this problem is 125 by tan 36, which is what? It is 172.05 Newton. So we saw for a single rigid body, how else could we have solved this? We could have simply taken this free body diagram. We could have applied sigma fx equal to 0, sigma fy equal to 0, sigma m equal to 0, as we have been doing. M about the z-axis equal to 0. This we could have applied and we could have still found the same answer. In addition to finding these two also, N2 and N1 also we could have found there. But what does our question ask? What should be the P to keep this in equilibrium? We are just trying to relate that. So we have, without doing this, we just drew the active force diagram and applied the principle of virtual work to solve this. So I hope that is clear. Now when we make the systems more intricate, we will be able to see that virtual work principle actually pays off. It is much better for the analysis because in the case of interconnected rigid bodies, we have to apply this condition to each and every conceivable subsystem, meaning each and every rigid body. So if there are 4 rigid bodies and I have to apply this condition, I have to apply it 12 times. Whereas if I have 4 rigid bodies connected, I draw the active force diagram without dismembering it. I just have to write one equation and I can get the solution, provided the system has 1 degree of freedom. If it has multiple degrees of freedom, I have to write multiple equations. But currently we are dealing with only single degree of freedom systems. In such a case, this will be ridiculously fast to write and analyze the equilibrium of the system. So that is the benefit of virtual work. So I hope that is clear. Are there any questions at this stage? Actually, we have not delved much into interconnected rigid bodies till now. I understand that. But I was trying to form a firm base so that when we go there, it doesn't create any problems. So I take it that this is clear. Okay. Yes, please. Go ahead, Mr. Krishnan. Yeah. It is from the geometry. See, I have a triangle like this. Essentially, I have a triangle formed like this, where this is L, this is theta I have been given. So for the bar, if this is my bar, this is my bar, then I can consider the weight to be acting here, right? So this distance is what I have calculated as h, and this distance is what I have calculated to be d. Now from the geometry, if this is L, then this is L by 2. Because we are considering weight, weight will act on the centroid, right? So this is L by 2. So can you see that h is nothing but L by 2 sine theta from the geometry? At the same time, if I take the whole triangle, I am able to see that d is nothing but L cos theta. Is it clear or something is unclear? Clear? Okay, fine. So like this, why we are trying to do this is, see, if we take h, if we give virtual displacement to the mass by h, and then we give virtual displacement to the load P by d, we cannot relate it to the same equation unless it is in one common denominator. For example, if we have two vectors, both have to be represented with respect to the same basis vectors for us to add or subtract them. Similar to that, we have to have a common representation in the in for terms of delta, in terms of theta, in order to equate them. That is why we did this. Now let us just delve a little bit into the energy aspects also. Actually, it has been discussed in much detail in the lecture, so I won't delve much into it. I'll just touch upon it. What this says is, now we have seen that sum of delta W external equaling 0 is my principle of virtual work. Now for conservative systems, I can have elastic potential energy for a spring, for example. If I have a spring like that, and mind you, if I were to elongate this spring by say this amount, delta x, now we know that a spring invariably opposes the offers resistance to displacement. Meaning, if I compress the spring, it will push to get to the equilibrium position. If I elongate the spring, it will again pull. That is the nature of the force induced in the spring and the displacement are invariably opposite in nature. I have given a displacement like that, and the force that sets up in the spring is like that. So it is always negative. Now, in case of a spring, let us just, now we know that force in a spring is given by kx, where k is the stiffness, x is the actual displacement. Now this actual displacement, a spring anyway will have some original length. That or at that original length, there is no force in the spring. So this is essentially the displacement of the spring, or I should say the elongation of net elongation or contraction. Now is this equation complete? No, I have to put a minus sign because it is invariably opposite in nature. This is the force in the spring. So if I give a positive displacement, it will give me a negative force. It will an induced negative force in the spring. Whereas if I give a negative displacement, it will give a positive force. So this net elongation, this aspect is very important because in cases we will be able to see that the spring, it is given that the unstretched length of the spring is something. So that will be our starting point. Only from there we are supposed to calculate this x. We should not take the entire uh, length to be x, meaning this x which we have put here, displacement, and this is force which we have put, we should not put it from here. This is just the unstretched length of the spring. Only after that unstretched length is elongated is my x actually considered. I hope that that is clear. So in such a case, if I draw my force versus displacement for a spring, I'll be able to see that this is slope is nothing but k, this is force, and this is the actual displacement. So the potential energy of a spring is given by half kx squared. So energy can never be negative, whereas work definitely can be negative. Okay, so because we can see here, whatever be the nature of x, it gets squared. So energy is invariably a positive quantity. How we relate energy to virtual work is that it so happens, be it gravitational potential energy or spring potential, elastic potential energy, it so happens that the change in the potential energy is equal to negative of the work done. So this is how we will be relating. The same holds for gravitational potential energy also. And how this comes about, the derivation for this, you can just refer the lecture. I will show the application of this, what is the consequence, how we go about applying this. So in such a case, we can also cast this as change in the uh, potential energy to be 0. And it so happens that a system will be, what are we saying here? That the sum total of all the virtual work done is 0. And by energy, invoking the energy principles, we are saying that our change in the potential energy is equal to 0. What does this imply? If I have a potential energy of a system denoted by V, change means the derivative. So V dash equals 0 gives me an equilibrium condition, meaning the first derivative equal to 0 gives me an equilibrium condition. So if V, being a scalar function, is denoted by some coordinate, it means that its extrema, either the maxima or minima, it represents a position of equilibrium. That is what this means. So with that background, let us analyze this question. So we have been given that the potential energy of a mechanical system is given by this. So the potential energy is given by 4 theta cube minus 3 theta squared minus 8. It's a scalar equation in terms of theta, where theta is the independent coordinate, meaning theta is the degree of freedom for that system. The value of theta in radians for which this system attains unstable equilibrium is what? Is what is asked. So let us see what that is. Now the potential energy, we need not write half kx squared and mgh. Let me just write this also. This is our gravitational potential energy, as we have been seeing right from physics classes in high school. So what this says is, I need not analyze some system. They have directly given me the expression, scalar expression that denotes the potential energy of the system, which is given to be this. Now, if I were to graph this out as a function of theta, v, it will have some curve. So what this is saying is, each of these positions are representing positions of equilibrium. It's a different thing whether it is stable or unstable. When will the equilibrium of a system be stable and unstable? So the condition equal to 0 equilibrium configurations. Whereas for stability, system is stable when V reaches its minimum value. At the same time, system is unstable when V reaches its maxima. So when we equate this, we will get stationary points. We will get all these points. But we have to analyze which is the point where we actually have the system reaching a maxima. That is where it will be unstable. And that is what we have been asked here. We have been asked when will it reach unstable equilibrium. So first we need to find out when will it reach equilibrium. So for that delta V equal to 0 we have to do. So delta V is given by 12 theta squared minus 6 theta. From here I have to equate this to 0 to get the stationary points. What will this give me? Theta into 12 theta minus 6 equals 0. So therefore theta is either 0 or theta is half. So I have got two positions now. Two positions of the system with respect to theta where my potential energy reaches a stationary point, meaning the slope becomes 0. Extrema, either minima or maxima. Now I have to analyze which of these is actually stable and which of these is unstable. Unstable meaning even with a slight perturbation, the entire system will collapse. Stable meaning even if I give perturbations, it will return to its original shape, original configuration. And this has been discussed with enough examples in the lecture, so I will not delve much into that. I will show the application part of that. So for this, for checking maxima and minima, what is the condition I have? V double dash, if it is greater than 0, it implies it's a minima. Why? Because the curvature will be like that. It's a positive curvature. This we know from mathematics, basic maths. Similarly, if V double dash is less than 0, it implies it's a maxima. Because the curvature will be like that. This will be negative. So let us calculate V double dash. What is that? It will be, I essentially have to differentiate this equation again. This will be 24 theta minus 6. And I have to try out these stationary points. So V double dash at theta equal to 0 is what? It is negative. And V double dash at theta equal to half is coming out to be positive because it will be plus 6. So I have identified a point where my second derivative is negative, which implies that it is a maxima, which implies that my system is unstable when it is a maxima. So what is the answer? Yeah. So what is the answer? Theta is, what was it? At 0 it became, right? Yeah. 0 radians is my answer. 0 radians or degree, it doesn't matter, both are same. Okay, so this is how essentially now what we'll be doing is in this question we have been given in the yeah uh, Dr. Tamar, could you mute your mic, please? Okay. Yeah, so what we have done in this question is we have once we have been given the equation for the potential energy of the system, we have analyzed whether it is stable or unstable. But mostly questions won't be like this. We will have actually a mechanism for which we have to write this equation and then find out whether what is the equilibrium configuration and whether it is stable or unstable. So let us go about doing that. Okay, so now let us solve this interesting problem. A straight rod is connected to a linear spring of spring constant K at A. So I have a bar like that, and then I have connected it to the spring, and this is pinned at D and is loaded with a force shown P here. And I can see that this is 1.2 B, this is B. Okay, now this is given to be theta, and it is pivoted here. The rod is pivoted. Was there any question? Okay. The rod is pivoted over the pin support and is free to rotate about B. The unstretched length, the spring is unstretched when the bar is horizontal. What does that mean? That when the bar was like that, and then here we have the pin. So here in this configuration, my spring was unstretched. I'm sorry, I can draw it better 1 minute. It's like this, and then here I have that spring. So this is my unstretched configuration. This is when theta is equal to 0. So and we have been asked to ignore the frictional effects and mass of the assembly. So let us go about looking at how to solve this problem. What have we been asked? Which of the option correctly represents the net elongation of the spring in terms of B and theta? So what are we trying to see? We know that force in a spring is minus kx. Here we have been asked to find this net elongation x in terms of B and theta from the geometry of the problem. So let us see that, how to go about that. Now let S be the unstretched length. I can see that this is S, while this is B, this is 1.2 B, and this is also B. We have been given here that this vertical distance is also B, right? So can I calculate the S from here? From geometry, S is nothing but B root 2. I can see that by using Pythagoras simple. I can see this. Okay, so I have got S. Now I have the configuration of the deformed assembly like that. I have the configuration like that, while this is where my pin is, and now it is connected like that. The spring is connected like that. Okay, so let me call this S1. Now I can see this is 90 degrees. Screen is not getting updated. Are you able to see it now? Is it still not getting updated? Could I just see it? Okay, okay. Okay, because it is important. Thanks, Mr. Anish, for pointing this out. In case if it is not getting updated, please let me know so that I hope you are able to see it now. So this is theta. Again, this also becomes theta then. So what is S1 is what we have been asked. So this is B, that is also B. Now in this triangle, by means of geometry, can I find out what S1 is? If I write this angle, what will that angle come out to be? Let me call that some alpha. I know that alpha is 90 plus theta by 2. I hope that is clear. I have just calculated this angle and taken the half of that. Why half? Because this is also B, this is also B. It's an isosceles triangle. So perpendicular will naturally be the angle bisector. So I have alpha is 90 plus theta by 2. So from this triangle, from that triangle, I can write, I know that this angle is 90 degree because I have drawn the altitude here. So this is 90 degree. This is B and I have this angle as alpha. So can I write this distance? What will that distance be? It will be, so if I take sine 45 plus theta by 2, it will be S1 by 2 by B. I hope this is clear what we have written. Okay, I hope that this is clear. We have taken sine of this angle, which means this is S1 by 2 by B is what we have taken here. So what does S1 come out to be from here? 2B sine 45 plus theta by 2. I have got S1 in terms of theta here. And I already have an expression for S. So what is my net elongation? Net elongation is nothing but S1 minus S. It was here. Net elongation is nothing but S1 minus S, which is 2B sine 45 plus theta by 2 minus B root 2. So this is my X for the spring. This is my X with the understanding that force in the spring is minus Kx. So for that minus Kx, this X is this quantity here. So let us look at the options. So 45 plus theta by 2 and this is sine. So I have 45 plus theta by 2, 2b. This is correct. Now we have been asked which of the options. So there could be more than one. So what is the difference that we observe here? Sine has changed to cos. So now we know one relation that sine of, or rather sine of, we not write that, we write cos of 90 minus a is nothing but sine a. So if I take this quantity to be a, so sine of 45 plus theta by 2 is same as cos of 90 minus 45 minus theta by 2, which gives me cos of 45 minus theta by 2. So by that this thing we are able to see that cos of 45. Option A is also giving the correct elongation of the spring. So I hope that that is clear. Okay, so all right. So we have got the actual elongation in the spring. So can we calculate the spring force? Now that we have got this, what the spring force will come out to be? Spring force is F S is minus K X, which means it is minus K into this quantity. So this is my spring force. In my configuration given, how is it acting? How is the spring force acting? It is acting like that. Because this is getting elongated, so it is acting like that. So I may well replace my system with a system like that, where this is the spring force and this is my P and this is theta. Because spring, whatever displacement I give, if theta increases, my Fs acts in the opposite direction. So the contribution of the spring, the virtual work contribution of the spring is invariably negative. Okay, now look at the next question. What is the equation in terms of BP, dk, p and theta that must be satisfied for this assembly to be in equilibrium? When this will be in equilibrium? When the sum of all the external virtual work contribution is 0. What are the active forces? We have already drawn the active force diagram. Fs and P are the active forces here. Okay, now I think it is, I don't know, there's a lag. I apologize for that lag. There is some, okay, anyway. So we have drawn the active force diagram. We have already been told that we have to ignore the mass of the assembly. So essentially mass doesn't come into my active force diagram. So now all I need to do is to relate this. If I extend this, and let us say that I call this, let us say I call this distance h. Now when theta increases, when I give delta theta, a positive delta theta, or rather a clockwise I should say, when delta theta is positive, P does positive virtual work, Fs does negative virtual work. I hope that that is clear. So for this force, we have got the expression. Let us get the expression for h. What is h? It is nothing but 1.2 sine theta. 1.2 b sine theta. Why? Because this is b. This is given to be b and this is, sorry, this is 1.2b. Sorry about that. So if that is 1.2b, we can see that h is nothing but 1.2b sine theta. So what is delta h? 1.2b cos theta delta theta. And we have said that we will invariably consider the magnitude and then assign the sign based on the physics of the problem. And physics we have written over here. So we will assign the sign based on that. Although it comes out to be positive, I am still writing it for clarity. So I have got this. Now have I got everything that I need? How do I write this virtual work expression? It will be P delta H minus Fs delta X equal to 0. Now we have got the expression for delta H. P is P only, which we have applied. For Fs, we have got the expression, which was over here. we have got the expression for Fs over here. What we have not got is delta x. So we have the expression for x, we just have to differentiate that. So let us do that. We had x equal to this. Let me copy this and let me put it here. X is this, therefore delta x will be 2b cos 45 plus theta by 2 into delta theta by 2, which gives me delta x to be b cos 45 plus theta by 2 delta theta. And we said we will consider the magnitude. So now I have all the expressions that I need to write the principle of virtual work. For equilibrium, I have to write delta external sum equals 0, which gives me P delta H plus P delta H because it does positive virtual work minus Fs delta X equal to 0. Or what is delta H we got from here? We found out that delta H was we have this expression, it is 1.2 cos theta delta theta. So let us write that. This 1.2 b cos theta delta theta minus what is the expression for Fs? We have this to be the expression for Fs. So let us take it there. Actually, we have already accounted for that. So for that minus we have already accounted here. That is why I'm not writing. I hope that doesn't create any confusion. If there is a confusion, please do ask. This is Fs into delta x. We have got delta x over here. Into delta x equal to 0. This entire thing, this is the total virtual work contribution of all the active forces in the system, and this goes to 0. Now it's just a matter of solving this. So let us quickly do that. It will be 1.2 p b cos theta delta theta, and then I'll take the rest to the right hand side because I have a negative here, so I'll just take it to the right. So it will give me, I'll multiply this, this, and this. So what will I get? 2k b squared sine, let me say 45 plus theta by 2. Let me define this to be a for brevity. So what will this come out to be? It will be 2k b square sine a cos a minus kb squared root 2. No, it's not complete. 2kb squared sine a cos a delta theta minus kb squared root 2 cos a delta theta. I hope this is clear. Okay, so from here, if I simplify this, I get b cos theta delta theta equal to I'll take this 2 and then sine A cos A. So what can I write? 2 sine A cos A is nothing but sine 2A. Sine 2 theta is 2 sine theta cos theta. So I'll just write this as kb squared sine 2A delta theta minus kb squared root 2 cos A delta theta. Okay, now let us substitute back. We had taken A to be this. So 2A will be 90 plus theta. Therefore, sine 2A will be sine 90 plus theta, which is nothing but cos theta. A little bit of trigonometry. So with that understanding, if I just take this equation again and I put it here, and then now I substitute, it gives me 1.2 pb cos theta delta theta, and then I have just now I have seen sine 2a is nothing but cos theta. Sine 2a is coming out to be cos theta. So I'll just put cos theta there. So it is kb squared cos theta delta theta minus kb squared root 2 cos a delta theta. Let me keep that in terms of cos a. Finally, I will replace. Now, what is it I want to get from this problem? What does it ask me? What is the equation in terms of this that must be satisfied? So we can see that all the theta terms have been grouped in one side and all the other constants have been grouped on the other side. So let us go about doing that. So if I divide this entire equation by this cos theta delta theta, what will happen? Essentially, from here I'll remove this. This also gets removed, and this is cos theta. Delta theta gets removed here. I hope that is clear. Now, further, what I can do is I can divide this by kb squared. Kb squared. So this will give me 1, and this just gets removed. And here b and b squared cancels out. I have 1b in the denominator. So I have got 1.2 p by kb equaling 1 minus root 2 cos a by cos theta. Now if I replace for a, what will I get? 1.2 p by kb equals 1 minus root 2 cos. How did I define a? I defined this as 45 plus theta by 2. So let me just put it there. 45 plus theta by 2, or this by cos theta. So this is my expression. What does this expression give me? This expression gives me the condition to be satisfied for this system to reach equilibrium. Which system? This system. Given a specific k and this distance b and a force p, under what theta will it reach equilibrium is what we are trying to analyze. So once we have to devise a mechanism of this sorts, where if I apply P, I want theta to stop at some particular angle. Appropriately, I will be selecting the spring stiffness for that system. This is the basic idea behind designing mechanism. So that is where this comes in handy. That is the broader perspective of this. So I have got this as the answer. So let us copy this and see which answer is correct. This is the answer I have got. So 1.2 is 6 by 5. So naturally, these A is not the answer. So let us see what else matches. 1 minus root 2 45 plus theta by 2. So I can see that B matches. So if B matches, D won't match. Now we know again the same relation that cos of A is nothing but sine of 90 minus A. If we apply that, we will be able to see that 90 minus 45 minus theta will come out to be this. In actual practice, both mean the same. We just have to derive one of them. This question is given with the purpose that you also brush up your trigonometry as well as you go about solving, because that is very essential to capture the movements of the mechanisms. So I hope that that is clear. So we have got one expression which satisfies the condition for equilibrium and gives us the relation between active forces and the degrees of freedom. So let us look at the last question, what it says. The assembly attained equilibrium when theta measured 64 degrees. By some means, we have measured that it is 64 degrees when this attained equilibrium. What must have been the magnitude of force P applied at C that caused this, if it is known that the spring stiffness was this and B was this? So it is simple substitution. What we have been given is, what is P? When theta was 64 degrees and yeah, this notes anyway, if you are not aware, I am uploading the video and these notes to that Swayam portal. If you go on the left side, on the bottom, are you able to access the videos that I'm uploading? Can you just tell me that, Mr. Krishna? Yeah, so wherever you're seeing that video, in that same, there is a folder, there is a Google Drive folder where I'm uploading these notes also, where whatever I'm solving. So from there, you will be able to easily get it. You can access for the previous ones also from there. Okay, so I hope that that is clear. Yeah, and K is 25 Newton per meter. B is given to be 0.35 meter. So this is not much exciting. Anyway, I'll just do this. P is KB. K is 25 into 0.35, or let me do it like that. 1.2 pi P by K into 0.35 gives me 1 minus root 2 cos of, because it is theta by 2, so it will come to cos of 64 degrees. So therefore P, can we evaluate P from here? To root 2, 1 minus 1. So this comes to 2. So I hope the calculations are fine. What this tells us is, when we had a system like this, we had a system initially like this, where theta, when theta was 0, the spring was like that and it was unstretched. Then we applied a force P to that system. We applied a force of 2 newtons to that system, where we knew K and we knew B, and it came to equilibrium at theta equal to 64 degrees. So this will be helpful for us to design mechanisms for one particular application in the broader scheme of things. So are there any questions about what we have solved? See, most of what we have solved is geometry only, but it is essential to understand this so that we are able to solve questions given in the assignments also, because those also will include geometrical interpretations. So are there any questions about what we discussed? If there are, please go ahead and ask. In any case, I'll move on to the next question if there are none. Okay, let us look at this problem. What this says is, we have we have a slot where there is a roller. So this roller can move only like that. And then to that roller, we have an oddly shaped bar that is connected, whose center of gravity is here at a distance of 3b by 5, with the understanding that this whole length is b. So 3/5 of that b is where the center of gravity is coming. If this was a rectangular bar, it will be at b by 2. Since this is wider going downwards, the CG gets pulled somewhat and it is at a distance of 3b by 5. So this is connected to a link, a massless link, which has a spring. Now this thing can rotate. When this was straight, it would have been like that, in which case this theta would have been 90 degrees. And in such a condition, the spring would have been like that. Now the spring has elongated like this. So I hope that that is clear. Elongated till this point. Okay, with this understanding, let us read the question. An oddly shaped bar of mass m, so this has a mass of m, is connected to a roller C which is free to slide. A thin massless bar AB, so this massless bar is there, is connected to the plate and compresses the spring. Why this compresses? Because the spring's other end is put here. Now when this bar goes down, naturally the spring will get compressed. So I hope that that is clear, because when this was straight, this point A would have been here. So the original length of the spring would have been here, would have been like that. Now since A is coming down and this point is fixed, the spring is getting compressed. If you have any questions about this configuration, please go ahead and ask. So the linear spring gets compressed when the plate falls. The spring is uncompressed when AB is perpendicular to BC, meaning when this oddly shaped bar was like that, and then we had the pole like that with point A here, that was the original length of the spring. So we saw in the previous question, we have to calculate original length and final length, and the difference of the two gives us the net elongation, which causes the force in the spring and subsequently contributes to the virtual work. The mass of this is 3/5. That is what we saw. So let us look at the questions now. Which of the following correctly represents the gravitational potential energy with respect to the datum and the positive coordinate directions shown? So we have been given that this is my datum and this is the positive coordinate direction. So gravity acts this way. So if this is my center of mass, this becomes my h. This distance is h for mgh. Naturally, it is below the datum in the negative direction, so it will be negative, no doubt. So at one instant, we can see that the third and fourth options are not correct, because gravitational potential energy, according to this datum and positive coordinate axis, it has to be negative. So Vg is nothing but mgh. Now h in this context is like that. In this context, h is like that. So h is nothing but so if I take this triangle, there, I have this as 3b by 5. I have this angle as theta. This is theta. So naturally, this also will be theta. If that is theta, I can see that this will be 90 minus theta. So I need this distance h. That is h. So it is nothing but 3b by 5 sine 90 minus theta. But we know 90 minus theta is nothing but cos theta. So therefore, h is minus 3b by 5 cos theta. y minus, because my positive coordinate direction is like that, my datum is like that. Datum meaning y equal to 0 line is here. So I have to go down to map it. That is why it is negative. So Vg for the problem is minus mg 3b by 5 cos theta. If I write it neatly, it becomes minus 3 mgb by 5 cos theta. Minus 3 mgb by 5 cos theta. So B is our answer. Okay, so far so good. Which of the following expression correctly represents the elastic potential energy in the spring? Now we saw what is elastic potential energy in a spring. It is given by half k x squared, where x is net elongation or compression. Now all we have to do is calculate what that would have been. In the original configuration, let me just add a page here. Sorry. Just a moment. Consider that bar was like this, the oddly shaped bar. It was like that initially. So this is where it is connected to the spring. This is my massless bar AB, and then my spring was connected till this point. So this is my original configuration. This is why it becomes essential in principle of virtual work to visualize how the original configuration is and how it moves about. So let me call this distance S. So S is the undeformed length. Okay, now what happened is this thing rotated. It rotated like that. So this came about like this. And then this point has come here. Take it that it is straight, but the spring goes only till that point. Now what will happen? This A would have come here. That point A would have come here. But it is constrained to stop here. So naturally this becomes the final length of the spring, S1. And this is X. Is it clear? This is the entire uh, key aspect to the problem. Once we visualize this, everything else is very simple. So once this rotates like this, we are able to see that S dash plus X makes up S. This is the final length of the spring. This is the initial length. So it underwent a compression of X. Now can we calculate what X is the question. We know this triangle where this is given to be theta and that distance is given to be B. So we can easily see that X is nothing but in this is my X. This distance is my actual compression in the spring. So in this triangle, can I see what this is? Let me take it like this, where I have this to be theta, this is B, and this is X. So I have X is nothing but B cos theta. So I have X is B cos theta. Therefore, PE is half K B cos theta the whole squared, which comes out to be half KB squared cos squared theta. So this is my elastic potential energy stored in the spring, half KB squared cos squared theta. Okay, so far so good. Now, are there any other active forces in the system? We have been told that everything else is massless, frictionless. So our active force diagram, active forces is the spring force and weight. So these are the only two active forces. Now we have already derived what H is. In fact, we have already derived what the gravitational potential energy is. Similarly, we have derived what the spring potential energy is. So what is the total potential energy of the system? Energy is a scalar quantity. It can simply be added. Kb squared by 2, or rather let me write it like that. V is V elastic plus V gravitational. So what is this? Kb squared by 2 cos squared theta minus 3 mgb by 2, sorry 5 cos theta. Now we have written the entire expression for the potential energy of this system. If you remember, we solved a problem where the expression of V was given in terms of theta, where we found out maxima and minima. There we were given this expression. This, we have actually derived this expression from the mechanics of the problem. Now once we have derived this, it is easy to see what to do for it to satisfy equilibrium. We saw that for it to attain equilibrium, what is the condition? Change in the total potential energy has to go to 0. So we just need to differentiate this and equate it to 0. So let us do that. Copy. So delta V, which is nothing but KB squared by 2, and I have to differentiate cos squared theta with respect to theta. So what will that give me? 2 cos theta into minus sin theta delta theta minus 3 mgb by 5 minus sin theta delta theta. And this I'll equate it to 0. Now mind you, when we write the energy, we have already accounted for the sign. When we wrote mgh, we have already accounted for the sign. So here we need not take the magnitudes as opposed to the force method where we actually took the magnitude of the virtual displacement. Then from the physics of the problem, we analyzed whether the active force is doing positive work or negative work. Here we need not do that. We simply differentiate this and equate it to 0. So what will this come out to be? It will be minus kb squared cos theta sin theta delta theta plus mgb by 5 theta tau theta equal to 0. This is the expression we have got. Now we can simplify this by taking it to the right side. This equal to this. So I have taken this to the right side. Delta theta gets cancelled. Sin theta gets cancelled. And when I took it to the right side, I have to remove that minus. So this gives me cos theta is nothing but 3 mgb by 5 kb squared, or cos theta is 3 mg by 5 kb. So this is how this system functions. Now let us say this was part of some mechanism. This oddly shaped bar had to be supported, and we had a constraint that this theta should not go less than 60 degrees. Then we can appropriately find k so that this expression is satisfied. That is how we go about solving. So 3 mg by 5 kb is what we've got. Let us look at the options. 3 mg by 5 kb equal to cos theta. So we have got this as the answer. So are there any questions? Is it clear? Because the current assignment would be having a lot of questions on springs, energy. So is it clear on how to apply the energy principles? If there are any questions, essentially what we have to do is, first we have to look at the original configuration. Originally, when the spring was unstretched, how it was. Then in the current configuration, how it is. Difference of the two will actually give us the net elongation in the spring. Once we get the net elongation, we can simply write the potential energy, elastic potential energy of the spring, along with the other components, other active forces that have contributions. Take the derivative, equate it to 0. This is by the energy method. Other way to solve this is, I could have taken this, since the spring is getting compressed, my force will be like that, but my displacement is like that. So the kx delta x is what my force would have been. Using the force method, by force method, if I were to solve this, instead of the energy approach, if I were to take the force approach, now I know that Fs is minus kx. What did we do? We wrote the spring potential energy as half kx squared, and then we took its derivative, which is nothing but kx delta x. Here we write the force, and then we take the virtual work as Fs delta x, which is nothing but minus kx delta x. So we can see that both give us the same quantity, with the understanding that the work done is the negative change in the potential energy, which we discussed initially. So both mean the same thing. That is why we are getting the same answer. Solving this by the energy approach gives us an additional benefit that we will be able to see whether we will also be able to analyze the state of equilibrium of the system, whether it is stable or unstable, and so on. So is this clear? I hope that this is clear. So if there are any questions, please do ask. In the meantime, let us look at this question. A uniform plate shaped like an equilateral triangle with side B, one of the sides is B, so it's an equilateral triangle, so all the sides are B, is suspended with one vertex. On one vertex, we have a massless string, and the length of that string is also B, and it is nailed to the wall. The length of the string makes an angle theta with the vertical wall. So we have the string like that, and then this angle is theta, what we have been given. So the mass of the plate is m, and this is a uniform plate. So centroid of the geometry coincides with the center of mass of the object, and gravity acts in the minus y direction. And this is given to be the datum. So what we have been asked to write now, which of the following correctly represents the total potential energy of the system with respect to the datum and the positive coordinate axis shown? We know this doesn't have any mass. So the only mass is the mass of this plate, which is acting like that. So we have only one active force in the system, which is acting at the centroid. Now, what is potential energy, gravitational potential energy? We know it is mgh. Now, mass is given to be m. All that is pending is how to calculate h. So that is what this question waters down to. So let us look at that. Now, if I were to, I know my center of gravity will be somewhere here. How do I locate the center of gravity for this object? Essentially, for an equilateral triangle, if I draw the perpendiculars, the intersection of that gives me the center of gravity or center of mass instead. So, and for an equilateral triangle, I know that one of the vertex angle is 60 degree. So if this is 60 degrees, this is 60. So naturally this becomes 30. And what is this distance? When I draw a perpendicular like that, this distance becomes, it is b by 2. In such a case, can I calculate what the distance, the green distance s is? S is nothing but, so from the figure, s is nothing but cos 30 is giving me b by 2 s, or s is nothing but b by 2 cos 30. So cos 30 is root 3 by 2. So essentially s will be b by root 3. Okay. Now, what is this h actually? This h is the distance, if I take a line like that, which is parallel to the datum. Let me make this a dotted line. So this is my h. This distance is my h. Now I can divide that into two components. I can say this is h1, and then the rest of the distance I can call that h2. So essentially h is h1 plus h2. Okay, h is h1 plus h2. Now from the figure I can see that h1 is nothing but b cos theta. In this triangle, this is theta, this is b, so this is b cos theta. That is clear. Now I have to calculate h2. For that, what I have to do is, let me draw a line like that. Or let me take a new sheet and draw it. Just a moment. So I have the triangle like that. And then this distance I know, this is s. Now I draw a parallel line like that. I know this angle is 30 degrees. From the problem, I know this is theta. So naturally, this also becomes theta. Then what will this angle come out to be? This is 30 minus theta. I hope that is clear. In such a case, I have this to be the figure, and this is my h2. Can I see from this triangle that cos of 30 minus theta is nothing but h2 upon s, or h2 is s cos 30 minus theta. So that is all there is to the problem. Now we have calculated h2 and h1. So h becomes plus S cos 30 minus theta. But the answer has all been given in terms of B. So we have to substitute S equal to B by root 3. So let us go ahead and do that. I'll just make a copy of this, put it here. H is P cos theta plus P by root 3 cos of 30 minus theta. Now I know cos A minus B is cos A cos B plus sin A sin B. So from there I can write this as P cos theta plus P by root 3. I can just expand that out. So it will be cos 30, which is root 3 by 2 cos theta plus sin 30 by 2. And if I take cos theta common, d cos theta, if I take common, it will be 1 plus root 3 by 2 root 3 plus b by 2 root 3 sin theta. So these two get cancelled. So 1.5. So h comes out to be 3b by 2 cos theta plus p by 2 root 3 sin theta. So once I have b, it is simple. We can write Vg. It is nothing but minus mgh equal to minus mg into this quantity. This is my gravitational potential energy for the system. Again, this is similar to what we got in one of the questions where they had given us the gravitational potential energy. They had given us the expression for the total potential energy. Here we have actually derived it. So let us see which option is right. 3b by 2 cos theta plus 2 by root 3 sin theta and with a negative sign. So I can see that my option C is correct. Now V I have got. What is the next question? It is for what value equilibrium will be attained if M is this and B is this. So what do I have to do? I just have to take Vg and equate it to 0, plug in the values of M and B and get the answer. So I leave that to you. I think I have run out of time, but I suppose I have at least, productively conveyed how to solve questions with the principle of virtual work by applying the force method as well as the energy based approach. So are there any questions in what we discussed? Is it clear? Do you want me to completely solve this problem or shall I leave it there? Yes, sure. That I'll do. So I'll just provide the calculation here and then I'll put in the answers for these. Okay. Okay. In general, if there are any questions other than that, you're welcome to ask. So today we saw how to go about applying the principle of virtual work. What is a generalized force system? What are consistent virtual displacements? And then we saw how to define active forces. We saw how to get degrees of freedom for a system. All this we combined and then we found that this is beneficial to solve problems for interconnected rigid bodies using the principle of virtual work. We understood how to write the principle of virtual work when there are springs or other things involved. What are the necessary aspects to focus on? And then we solved this for a single rigid body, which we could have done with force equilibrium also, but we saw that instead of applying three equations, we just could solve it with one equation. And this came in handy when we were solving problems with springs and other active forces. Once we are given the potential energy of the system, we know how to find out the equilibrium configuration. And based on maxima and minima, we can conclude whether the equilibrium is stable or unstable. After that, we solved some problems which had springs and other things. So since the assignment also has problems with springs, I hope that what we have discussed here will come in handy for you to solve them. If you have any further questions, you can ask now, or you are also welcome to ask that in the forum. So with that, I think I've concluded what I wanted to say. I have nothing further to add. So if there are no further questions, I'd call it a day. Yeah. Okay, so there was a query regarding why we take hogging and sagging moments, or rather the positive and negative bending moments, to be equal in order to arrive at an optimum section. Let us say that we have an overhanging beam like this with a constraint that A and B can be changed at our liberty, but the section has to be the same. The cross section of the beam has to be rectangle of fixed dimensions. In such a case, if we see, based depending on the ratio of A and B, our bending moment diagram will vary something like this. Either if B is much greater than A, then we'll have a huge positive bending moment, while the maximum negative bending moment will be less. Whereas if we were to reduce B, we will see that this peak will keep on reducing, and there is also a possibility that it might not even become positive. Now the thing is, why we go for optimum design? Essentially what we are trying to say is max in tension is the same as max in compression. Let us say that this is made of a material which can let us say that this is made of a material which can take maximum of 100 MPa. Now when we design this, we would like to ensure that the overall section of the beam is much lesser than 100 MPa, let us say 75 MPa. Now, if we were to have a case where B is much greater than A, we'll see that at this point, our stress will reach rather 90. And at these 2 points, it will reach somewhere around 30. At the same time, if I reduce this to a much lower extent, that is, if I increase the overhang, in such a case, I'll notice that the peaks at the negative bending moment side, the stress will peak to around 90, and at the tension side, it will just barely be around hovering around 20. Now, given that I can change A and B, but my section is still uniform, at best, what can I say that if I want the entire beam to have a peak stress of say 75, then I will adjust it in such a way, because these two are related. As soon as I increase this, as soon as I increase B, my positive bending moment increases. At the same time, my negative decreases. And when I reduce B, my positive decreases and negative shoots up. So if we have to hit a middle ground between these, we will say that we can equate the positive and negative bending moments and arrive at the optimum ratio of B by A, so that both the stresses experienced by the beam are hovering around 75, given that the maximum stress is 100 MPa. So this is the reason behind us taking the positive and negative and equating it so as to arrive at the most optimum section. So I hope that this is clear. I'll see you guys in the next session. Next Friday, we'll be discussing friction. So I'll see you then. In the meantime, if you have any questions, feel free to use the forum. So thank you. Thank you for attending.